Yeah, hi everyone. Good evening. I think I'm audible to all of you. Can you please confirm in the chat, guys, if I'm audible? Yeah, hi everyone. Good evening. I think I'm audible to all of you. Can you please confirm in the chat, guys, if I'm audible? Yeah, hi everyone. Good evening. I think I'm audible to all of you. Can you please confirm in the chat, guys,
Guys,
if
am I
I'm audible?
audible?
Hello. Yeah, hi everyone. Good evening. Yeah, hi everyone. Good. Please confirm in the chat, guys,
Guys,
if
am I
I'm audible.
audible?
Hello. Okay, so thanks for the confirmation, and we can start with the session, guys. So welcome to day 6 of our computer vision for developer series. So today we'll be discussing about the pooling layer and CNN architecture. So far, guys, I think we have completed so many topics inside convolutional neural network. We saw how convolution happens. We saw like stride paddings. Okay, these are the concept as well. Now today we'll be learning another interesting and very important concept called pooling layer, and we'll be also exploring different CNN architecture. Okay. uh, okay, real to animations world is telling your course is amazing. Thank you so much. Hello, I was a student of iNeuron. I applied for internship, struggling with a code. Can you help? Definitely I can help, Mishra. So you can just ping me on my LinkedIn. Okay, so definitely I can like conduct a meeting and I can help you with that. Okay, what kinds of questions you are having. So guys, now let's start with our session. So guys, this is the playlist. If you're joining for the first time, so this is the playlist here you'll be getting in my YouTube channel. So the playlist name is Computer Vision for Developers. So here we have already completed till day 5. Okay, and in my previous session I was talking about padding and strides in CNN. Okay, now we'll be talking about the pooling layer and CNN architecture. Okay, this thing will be understanding. Yeah, so before starting, guys, so please try to hit the like, all of you. Please try to hit the like if you like my sessions, and if you want these kinds of session more, guys, please try to hit the like. And if you're new to my channel, guys, please try to subscribe to my channel. So let's hit 50k subscriber, guys, as soon as possible. And I have very big plan here. I'll be coming up with actually different let's say playlist. And if you need anything else, guys, from my side, you can let me know. I'll also bring it here. Sir, kind of request for you to explain the code in detail because I'm intermediate for Python. Definitely, I'll take care of that part. Okay. And for Python, if you want to master the Python, guys, I also have another playlist in my channel called Python for AI. Okay. So this is the playlist, guys, you can follow. And I can promise you guys, after completing this playlist, you will pro in Python. Okay. You can develop any kinds of AI applications. So this playlist, I have more focus on the AI development. So you can see Python for AI. Okay, so if you go through the entire, let's say, playlist, you will be loving a lot. So those who are struggling with the Python, guys, I will suggest you go with this particular playlist, all of you. Okay. And if you only want to master the object oriented programming, so recently I have published one short video. It is around 5 hours. You can go with this particular video. So it will cover all the concept you need to master the object oriented programming in Python. Okay, so let's open up my board, guys. uh, and let me write down today's agenda. Okay, what are the things we're gonna cover? So agenda for today: the first topic will be exploring pooling layer. Okay, pooling layer in CNN. Then once we understand the pooling layer, we'll try to explore a different CNN architecture. Architecture like linet, pipe, let me write down, linet, pipe, and AlexNet. Okay, so these are the architecture we'll try to explore one by one. Okay, then in the next class we'll be talking about the backpropagation in convolutional neural network. Okay, this is another amazing and interesting concept. Even I saw like there are some interview also, they will ask you this kinds of question like how backpropagation happens in the CNN architecture. We'll also try to discuss it. Then we'll try to move to the transfer learning. Okay, we'll be working with the pre-trained model. All right. So first of all, let's start with the pooling layer inside CNN. Now, what is pooling layer, guys? So as you already know that, see, let me import one image. Let's say I will take this image. This one I can take. Yeah. So this is my, let's say, one image. So here guys, what we are doing here, we are doing the convolution operations, and how convolution operation happens, I think I already explained in my previous session. So if you are not sure, please try to check my previous session and try to come up with this particular session. Okay, so here let's say I'm having an image. The image size is 6 cross 3, 6 cross 6 cross 3. That means it's a RGB image. Okay, that means red, green and blue. Then here we are using filters, different filters. You can see we are using multiple filters, that means 2 filters, and we are doing the convolution operations. So after applying the filters, what we are getting, guys, we are getting something called feature map. This is our feature map, guys, FM, that means feature map. Okay, and we are combining the feature map, you can see. So this is my first feature map, this is my second feature map. That means the how many filters you are going to use. Okay, number of filters you are going to use, that particular number feature map you will be getting. Let's say here you are using 2 filters, you'll be getting 2 feature map. If you are using 3 filters, you'll be getting 3 feature map. Okay, if you are using 100 filters, you will be getting 100 feature maps. So that's how things works. Okay, and I already explained this part. Now, what is the problem with convolution? Let's try to understand. So this is the convolution, we already know that, but what is the problem? The problem with convolution. Okay, problem with convolution. See, the first problem you will be getting called memory. Okay, memory issue. And the second problem you will be getting so there is a name called translation, I think, translation variance. Okay, translation variance. Okay, so this thing I'll try to tell you. Okay, what is this particular concept? And first of all, let's try to understand the memory issue. Okay, how the memory issue happens if I'm doing these kinds of convolution operations. Okay, now see, let's say here we are using an image. So as of now, let's try to consider we are using, okay, we are using 228, sorry, 200. Let me take a new color. Let's say my image size is, let's say this is my image, and the size of the image is 228 cross 228 cross 3. That means this is the width and this is the height and this is the channel of that particular image. And on top of that, you are using 100 filters. Okay, 100 filters, 100 filters for the convolution operations. Okay, now tell me, guys, if I'm using 100 filters and the filter size is, let's say, 3 cross 3, 3 cross 3. Now what would be the feature map? Can anybody tell me what would be the feature map, guys? I think I already told you that formula, right? How we can calculate the feature map. So there is one formula, I think I already explained. So if I'm using 3 cross 3 filter, guys, on top of the 228 cross 3 image, so what would be the feature map? So feature map would be 226 cross 226 cross 3. Okay, 3. And how many feature map you will be getting, guys? Tell me. So let me write it here in a clear explanation. I can write it here. So it would be 226 cross 226 cross 3. And how many filters you are using? 100. That means how many filters you will be getting? You will be getting 100 feature map. Okay, 100 feature map. Now let's say if you are storing this particular value in a 32 bits float. Okay, 32 bits float. So what would be the like size? Tell me, what would be the size? Any idea? If you calculate, it would be around 19 MB, 19 megabyte. Okay, 19 megabyte. And this is for only one image, guys. This is for only one image. Now let's say you are having batch of image. Let's say you are having 100 image. Okay, 100 image, 100 training sample. That time if you calculate, it would be around 1.5 GB. Okay, 1.5 GB, more than 1.5 GB. Okay, now I think you are clear. Okay, why I have written the memory issue at the very first point. Because if we do this kinds of convolution, okay, if we do this kinds of convolution, what will happen? You will end up with actually very big feature map. You will be end up with very big feature map. Now you can tell me, sir, I can use the pad stride. Then stride is equal to 3, stride is equal to 4, then I can reduce the feature map. But what will happen? It will lose the information. I think I already explained in my previous day, right? So if you are using stride is equal to 3 or 4, it will lose the informations. It will lose the very, let's say, important informations from the image. Because what stride does, it will skip. Okay, it will skip some of the pixels. It will skip some of the features, right? So that's how we can reduce the feature map, but at the end you will lose some informations. Okay, then is there any other way we can like do this kinds of operation? That means we can reduce the feature map size, but still I can hold the feature information inside my feature map. Is it possible? Yes, it is possible. For that you will be using something called pooling. Okay, pooling in CNN. There is a layer called pooling layer. Pooling layer you'll be using inside CNN. Now how pooling layer works, I'll let you know. Okay. And now let's try to understand the second point. Okay, translation, this variance. Okay, this variance problem. So for this I can import another image. Let's consider this image. Translation invariance. Okay. Yeah. So now see, guys, here we are having a cat image. So this cat, you can see this is a right shift. Okay, right shift. And this cat, it is a left shift. You can see this is the same dimensional image, but this cat object present, it is the right shift and this is the left shift. Now let's say you are doing image analysis, or let's say you are doing the feature extraction. So what will happen, guys? Tell me, what will happen? Okay, what will happen? Can you see some unnecessary, like, I mean, features are there. Some unnecessary features are there. Why we need pooling? Okay, that is what I'm explaining now. So not a coder. Just try to like rewind the video and try to start from beginning. You will see that the first issue we have sorted out called memory issue. Okay. Now we're explaining the second one. Yeah. Now here you can see some other unnecessary information right hand side also. Okay. Because at the end, these are the information is not required to identify this is a cat. Yes or no? And yes, both images would be considered as a different image, because this one is the right shift one, this one is the left shift one. Okay, this is another issue. Now I can use pooling layer to prevent this kinds of issue. How? See how pooling layer works. First of all, let's try to understand. Okay, then I think your understanding would be clear. Let's try to discuss the pooling layer. See what pooling does. Pooling does downsampling. Sampling. Okay, downsampling. What is the meaning of downsampling? Downsampling means, let's say you have a bigger picture. Okay, after doing the convolution, the feature map you are getting. Okay, again this is a like a, I mean, some kinds of big feature map you are getting. If you are using padding, that time the feature map you will be also getting. This will be the same size of your input image, yes or no, right? Now if you apply the pooling on top of that, it will downsample that particular image, downsample that particular feature map. Okay, how? Let's try to understand. See, I think I showed you one image before. This one. This is the image. So there I was doing the convolution operations. Let's say this is my image, input image. So here this is my filters. Sorry, just let me. Okay, what happened? Just a minute, guys. Okay, I think I zoomed, right? Okay, now it is fine. Pulling down sampling. Now I think I will import the image. So here this is my filters. Okay, this is my filters, and here we're applying it and we're getting the feature map, FM feature map. Okay. After getting the feature map, guys, what I told you, we apply a non-linear actually function, which is nothing but ReLU. Okay, ReLU activation function we apply on the feature map. Okay, then after applying the ReLU, okay, after applying the ReLU, the feature map we usually get. Let's say this is my feature map we got. Let's say this is the feature map I got. I can take one image. Let's say this one. Let's say this is the feature map I got. This feature map I got after applying the ReLU. Now what max pooling will do, sorry, what pooling layer will do, see, in pooling there are some type. Pooling, there are some type. The first type is max pooling. Okay. Then second one is average pooling. Okay. And there is another one called global. I think global average pooling. Let me see. There are different poolings are available. Yeah, so global. Okay, global average pooling. Average pooling. So max pooling, average pooling, global average pooling. No, see, I think I can write like that. See, there is another pooling called global pooling. And inside global pooling, you have two types. One is a global max and other is global average pooling. Okay, average pooling. So these are like pooling types. Okay, I can write pooling types. Pooling types are available. Okay, now let's try to consider. Here we are applying the max pooling. Max pooling. Okay, after getting the feature map, we are applying the max pooling. Now after applying max pooling, guys, what I will get? Okay, after applying the max pooling, what I will get? See, in pooling we are having some parameter. The first parameter we have the pooling size. Pooling size. So usually pooling size would be 2, 2. Okay, pooling size would be 2, 2. That means, see, pooling is nothing but what? It's a matrix you are getting at then, right? And the size of the matrix would be 2 cross 2. Okay, 2 cross 2. That means, let's say this is your feature map, and here you have to do the pooling. So how many pixels? That means how many numbers you will be taking? Will be taking 2 cross 2. That means 1, 2 and 1, 2. Okay, that's why this is the size of the pooling. Okay, then you are having something called stride. Stride. So stride we usually take 2. Okay, 2 stride we usually take whenever we perform the pooling operations. Then there is another parameter called type of the pooling. Which type you want to use? Let's say as of now we are using max pooling here. Now see, what would be the result? Now let's say if my pool size is 2 cross 2, that means I'll be taking this matrix, and here I'm using something called max pooling. Now it will try to find a maximum value in this particular 2 cross 2 matrix. Now guys, anybody tell me what is the highest number here? See, mean pooling is also there, but mean pooling we don't use, okay, at the end, no coder, because mean pooling mean for you are taking the minimum value, okay, not the dominant value. And at the end, I mean, see, there are very less applications are available which is using mean pooling at the end. You can also write mean pooling here, but we don't use it. Okay, mean pooling we don't use it. Okay, so yeah, so here the most, I mean, maximum value is 6. Okay, you can see 6 is there. Now again, stride is equal to 2. That means this pixel it will skip, this grid it will skip, and it will come here. This matrix it will take. Now again, in this matrix, what is the biggest number, guys? What is the biggest number? What is the maximum number? It's 8. Okay, then again, stride is 2. It will skip this grid and it will come here. And what is the maximum value? It is 3. Okay, here you can see it is 3. Then again, it will skip this grid and it will come here. And what is the maximum value? It's 4. So this is nothing but your pooling result. Now can you see, guys, this particular feature map you had, now it has become downgraded. Yes or no? It has got downsampling. And now previously it was 1 2 3 4 5 1 2 3 4. That means 1 2 3 4 1 2 3 4. Sorry, now previously it was 4 cross 4. Now it has become 2 cross 2. That means half of the pixel it has reduced, and it has only taken the dominant pixel. Okay, dominant features. Okay, it has only taken the dominant features, nothing else. Let's consider this particular image. Okay, so here what is the more dominant feature, guys? So in this section or in this section, tell me. Let's say this is the first section and this is the second section. So in which section you can see like more dominant features are available? If I want to understand this particular image is a cat image, tell me. The first let's say part, or let's say the second part. Tell me quickly. Which is more dominant, the first one or second one? So let's say whenever you're doing the convolution operations, where you will be getting the, let's say, features? Definitely in the second one, right? So that's how things work. So let's say here you are getting some minimum number and here you are getting the highest number. That highest number you are taking here. This is called more dominant feature, guys. More dominant features. And that's how max pooling works. Without losing any kinds of informations, it can still, okay, it can still downsample your image and it can capture the meaningful features from the image. Okay, which you can't do with the help of stride. Got it? That's why max pooling is super important. Now, if you do the calculation, okay, it will take very less memory in the RAM, right? Hmm. What about background is black? See, again, background is black. Black means there is nothing, nah? No coder. See, background black means there is nothing. There is no features. It's zero value, nah, at the end. But whenever you have the features, that means there would be some number definitely, because previously I also showed you one image, nah? So here, let me take that image. This image I can consider. See, wherever you have the numbers, wherever you have the features, so it will have some numbers. You can see it will have some numbers. Okay, you can see some numbers are there, and wherever it is like nothing, there is nothing, it's a black, there would be 0. Now tell me, here you will be getting the dominant feature or here you will be getting the dominant feature? I can take a new color. This is the part 1 and this is the part 2. So here you will be getting the dominant feature, or here you will be getting the dominant feature. Tell me. This is the first part. This is the second part. Definitely in the second part we'll be getting the dominant features, because here we have the number. Okay, I think you are getting my point. Yes or no? Clear? So how many of you are clear, guys, this concept? Pooling concept. Why pooling is required? Now, if you have this kinds of problem also, if your image is present at the right position or at the left position, there is no issue. If you apply the pooling layer, okay, if you apply the pooling layer, it will automatically find the dominant features, okay, from the image. Got it? A very simple concept, but very powerful. Very powerful, because here you are reducing the computation, because the computation it is taking with these kinds of features, feature map, okay, the original feature map, and the space it was taking in the hardware, it was like very high. Okay, just try to consider whenever you are doing production grade training, that time you will be using lakhs of images, right? And there, if you consider the space, if you consider the like computational power, it would be like super high, right? But whenever I'm applying this kinds of pooling layer, you can see here we are downsampling that particular feature map easily. Here we are only capturing the more dominant features, and rest of the let's say value we are ignoring here at the end, right? Okay, got it? This is the idea. Now let me show you one visual representation. I think after seeing that, your understanding would be more clear. So I'll be following that same deep lizard website, guys. So here you can see there is another example called max pooling. So here, let's say I'll be taking MNIST dataset, and let's take a digit. Let's say I'll be taking 0. Okay. Now, if I play it, you will see that. Okay, if I play it, see, this was my original image. Now, after applying the pooling, it has downsampled the image, and still I can capture the informations whatever I have in my original picture, guys. Okay, you can see still it is present. Okay, so this is the work of a pooling layer, guys. Okay, at the end it will downsample the image. Okay, it will downsample. Let's say if your image is 24 cross 24, it will downsample by half. Okay, that means it would be 12 cross 12 that time. So what if someone else present in the background? Then what will happen? It won't the feature confuse. No, if someone is there now, if let's say if there is an image and someone is present in that image also, that means there is a feature. Okay, there is a feature, right? So it will only take that particular features, and rest of the background it will try to remove. Okay, I think you are getting my point. Because inside an image there would be like person, there would be background, there would be unnecessary things also. So clear, guys? Tell me this pooling layer, how pooling layer works. And always remember, guys, this pooling layer you will be adding. This pooling layer you will be adding after doing the convolution. After doing the convolution, you will be adding the pooling layer. So what is the architecture? Okay, what is the architecture of CNN? Do you remember, guys, the architecture of CNN? So maybe I have the architecture here. So this architecture, see, this architecture you can refer. See, so this is your input image. First of all, they applied convolution. That means conv layer, convolutional layer. After convolutional layer, okay, so whatever feature map they are getting, they are applying the ReLU. Then they are applying the pooling layer, you can see. Okay, then again convolution, then again ReLU, then again pooling, then convolution, ReLU, pooling. Okay, so this is the flow. It's not like that. First of all, you will be applying the pooling layer, then you will be applying the conv. Okay, it won't be working. Okay, that's how you won't create the architecture. So every architecture will see that people are applying convolution, then the feature map they are getting, they're applying the ReLU just to get the non-linear value. Then on top of that, they are applying the pooling. Okay, pooling layer. just to downsample the feature map. And that feature map, again, it will go another convolutional layer. It will again perform another convolution operations. It will apply the ReLU. Again, it will pass, okay, to the pooling layer. Again, it will do the downsample operation. That's how things will work. I hope it is clear, guys. Okay, always remember, after convolution, okay, you will be applying pooling layer, not before that. Robotics Hriday, hi sir, how are you? I'm good. What about you? All right. Now, some types of poolings are available, guys. Let's try to understand. I'll take this image. Okay, so I think I told you we are having some types. Let's say we are having max pooling. Then we are having right, max pooling. Then we are having average pooling. We are having global pooling. So inside that I have two kinds of pooling. One is global max. Okay. Another one is global average pooling. Okay, but if you see the frequently used, the max pooling and average pooling, I think I already showed you the max pooling. Max pooling means it will only figure out the maximum value. Okay, and what about average pooling? Average pooling, it will try to average. It will try to average all the number, and whatever number you will be getting, that would be the result. Okay, so that's how average pooling works. Very simple. Max pooling, it will take the maximum value. Average pooling, it will take the average. Okay, average. That's it. Hmm. And how global pooling works? Okay, global pooling, see, it will try to see the average for all the number, and let's say first of all it will try to take this average, then this average, this average, then this average. Okay, and which will return the biggest value, this will try to return that. Okay, this is called actually global average pooling, okay, or global max pooling. Let's say you have calculated pooling here. Okay, first of all you will do the average operations. Okay, then you will be getting a number, let's say n1. Then here you have done, let's say n2, then n3 and n4. Okay, now you'll try to see, let's say I'm using global max. So what would be the maximum value here? Okay, after calculating the average of all the metrics, so whatever will be having the like bigger number, that would be selected here. And what about global average pooling? It will again try to see the average. Okay, average, based on the average it will try to take the number. This is the difference. But most use one, the max pooling as well as the average pooling. Okay, this one. In any kinds of architecture, we'll see that people are using max pooling and average pooling. Okay, so global pooling is like very rare used. Yeah, thank you, Victor. Yep. Now let's try to see in a practical way how we can use this pooling layer with our CNN architecture. So for this, I'm going to open up my Google Colab. So let's open up. So I think remember guys, in our last session, we created architecture, right? We created CNN architecture. I showed you how we can create the architecture, how we can take the convolutional layer, how we can pass the input, how we can define the stride, how we can define the paddings. Okay, each and everything I already explained. So please try to check it out. So I'm not going to let's say explain that part second time. Okay, so here I'll just write pooling layer and CNN architecture. So let me just write pooling layer and CNN architecture, and all the resources is available in the description. So this is the GitHub, guys. So this is my GitHub, and I already published the resources here. So let me open it up. So this is the resource. So till day 5 I have updated everything. So here you'll be getting all the codes file and everything. It is available here. Okay, you can check it out. Now let's try to connect the notebook. Okay, let's connect the notebook. And here you are working with deep learning. Okay, that means this is nothing but deep learning architecture. Try to select the GPU as a runtime. Okay, I'll be going with free GPU. Now again reconnect. So let's import some necessary library. I think I already showed you these are the library we usually use. What is dense, what is contour, what is flatten. Okay, now this is the pooling layer, guys. Okay, if I want to use the max pooling, so there is a layer called max pooling 2D. If you want to use average pooling, there is a let's say layer called average pooling 2D. Okay, you can even search here. Let's say average pooling. Okay, average pooling in TensorFlow. So there is a documentation you can visit. See, average pooling 2D. This function you have to use. You can see average pooling 2D. Okay, you have to import it. If you want to use global, just search for global. You will see how to import the global as well. So all kinds of pooling are available in the like TensorFlow Keras. From there you can import it. Then sequential layer, and if you want to use any dataset, let's say as of now I'm using MNIST handwritten dataset. Okay, but I'm not going to train any model. I'm only just importing the data. That's it. Later on I'll show you okay how we can train the model. All right. Now if you want to load the data, that's how I can load the data. So training set and testing set. And if you want to see the shape of the data, it's 28 cross 28 and it's a grayscale image. That's why there is no channel. Okay, and 16,000 example you have in the training. Now that's how we can create the model architecture, guys. You can see this is the model architecture. So these are the layer are already common, guys. Okay, we have already implemented like this convolutional layer. Okay, convolution architecture. Only the change I have done, I have added the max pooling. Okay, you can see the pooling layer. And how to add, after doing the convolution you have to add the pooling layer. You can see max pooling 2D. First of all you have to apply the pool size, because I told you in max pooling we have some parameter. The first parameter you define the pooling size. Here I have given 2 cross 2 because this is the size we use, guys, 2 cross 2. Okay, and the second parameter you have the stride, and stride we also keep the 2. Okay, 2, you can see 2, and padding is equal to valid. Valid means here we are not using any kinds of padding. Okay, then again we are applying another convolution. Then here we are again applying another pooling. That means once you have done the convolution, try to apply the pooling after that. Okay, this is recommended. Okay, this is recommended because at the end you have to downsample the feature map just to reduce the memory complexity, as well as this invariance. I think there is a concept, I forgot the name. Yeah, translation invariance. Okay, this particular concept, because if your image is in the left shift or right shift, okay, that time you have to fix that with the help of pooling operations. This is the idea. Then we'll be doing the flatten. Then here we'll be adding the dense layer. Okay, then we can create the entire architecture. So this is the entire architecture. Now if I show you the model summary, you'll see that every time it will downsample the image. So let's say this is my original image. So after doing the first convolution, it will become 26 cross 26. Okay, 32, because here you are using 32 filters. Okay, here you are using 32 filters. Then again you are using max pooling 2D. That means half of the information it will downsample. That means let's say here you are having 26. Now it will become 13. It will become 13, and again you are using 32 filters. So that's why it will come 32 here. Then again you are applying another convolution. That means it will become 11 cross 11 because the filter size is 3 cross 3. Okay. Then again you are using another max pooling. So it will become 5 cross 5. Okay, I hope you are getting, guys, right? Then you are applying the flatten. Then this is the dense layer. Yes or no, guys? Clear? Which pooling is the best? See, I'll tell you. Try to use max pooling and average pooling. Okay, no coder. These two poolings are best. Okay, at the end. So most of the architecture you will see people are using max pooling and average pooling. These two do pooling approach. Yep. So till here, guys, are you clear? Tell me. If you are clear, guys, please write clear in the chat. Till here, guys, everything is clear. Let me know. Any question if you have, please let me know. Because now we'll be starting with the architecture discussion right now. Okay. First of all, we'll see the Linet 5 architecture. Now see, we have completed all the basics, okay, all the basic stuffs which we need to create an architecture, CNN architecture, okay. Now you are not going to face any kinds of issue to understand any kinds of architecture, okay. Now we can open up any research paper, we can see the architecture and we can easily understand, okay, what kinds of, let's say, architecture they're using, how many layers they're using, how many comp layers are there, how many max pooling are there, okay, how many, let's say, filters they are using, everything we'll try to understand. Yeah, so why stride is 2 not 1? Because to reduce the image size, okay, to downsample the image size, okay, no coder. Because if you keep it 1, so again it will go by grid, okay, and that's how we can't reduce the size, nah, that's why. Okay, now let's understand one amazing architecture, and this was the first architecture, guys, in CNN called Linet 5. Linet 5. So if you search for like Linet 5 paper, so this paper was proposed by Jan Likan, so he was the researcher, and he first of all proposed this architecture, okay, in CNN. So this is the paper, official paper. So let's open it up. So it is opening. So what I can do, let me just give you a walkthrough, okay, how we can create the architecture. Let's say here we have the image. We have the image, okay. Let's say we are using RGB image. So first of all, let's say this is the image size 32 cross 32 cross 3. So first of all, here we apply the convolution, okay. We apply, guys, what? We apply convolution. So let's say we'll be using different filters. One filter, two filters, three filters. Okay, here let's say we are using three filters, and this is nothing but our conv layer, conv one layer, okay, first layer. So after that, guys, what we'll do, we'll be getting a feature map. Here we'll be getting a feature map. So how many feature map we'll be getting? We'll be getting three feature map. Okay. So as of now, just to simplify, I'll just draw it like that. Let's say three feature map I got here. Okay. Three feature map I got. Now this thing I will pass it to the ReLU function, ReLU activation function. ReLU activation function to perform the non-linear value. Okay. Then what we'll do, guys, we'll try to pass to the pooling layer. Okay, we'll pass to the pooling layer. So this is my pooling layer. Pool layer. Okay. Then again, what we'll get the downsampled feature map. So this is my downsample feature map. Let's say this is my downsample feature map. Downsample. Let me write down, or I can write my feature map. Feature map. Okay. Then again, what I can do, I can pass this feature map to another convolution. So here I don't have the space, so let me draw it here. I can pass to another convolution. Let's say this is another convolution we are doing. This is another conv. So here I can draw it like that. I think that would be fine. Let's say this is another convolution layer. Conv to let's say second layer. So after that we are passing again where guys, again what we'll get, we'll get the feature map. Okay, and that feature map we can again pass to the pooling layer. Let's say pull to. Okay, then you can pass again to another convolution, again another pooling, again another convolution, again another pooling. But let's say I want only two convolution and two pooling. After that we'll do the flatten operation. Whatever feature map I will give, I'll try to do the flatten operation. Flatten operations. Okay, then I will pass to the where, to the fully connected network. Fully connected network. Okay, this is the fully connected network. FC. So this is the entire architecture, guys. Okay, CNN architecture we usually create like that. Clear, guys? Tell me. Can you tell me when you will be using the YOLO? YOLO, see, as of now we are covering the foundation of CNN. After that I will start with the image classification. It will take a few more sessions. Then I will start with the object detection. In object detection I will explain the faster RCNN, SSD. Then we'll start with the YOLO. Okay, maybe it will take 4 to 5 sessions. Okay. Standard book to study computer vision. There is a book I can suggest you. This is from NVIDIA. So NVIDIA Institute Computer Vision book. Deep learning books and reading. So let me see the image. So this book actually, guys. Okay, deep learning, theory, practical, neural network, computer vision, natural language processing, transformer. So this book, guys, learning, deep learning, theory and practicals. This is the name. This book you can follow, guys. This is like very amazing book, and it has actually all kinds of concept. Okay, and this is from NVIDIA Institute. They have written the book. No, after not 1 month, because here I am taking the regular basis class. Okay, so maybe after 5 to 6 days you can consider. Just 1 week. Okay, just consider 1 week. Okay, after 1 week I will start the YOLO. Yep. Okay, so that's how, guys, we usually create any kinds of CNN architecture. Okay, and it has convolutional layer, it has pooling layer. Okay, and it has dense layer, and in between we use ReLU activation functions. Okay, just to perform the non-linear operations. Okay. Now let me show you the different architecture. See, this is the first paper proposed, guys. The paper name was gradient based learning applied to document recognitions. So this architecture they proposed for the document recognitions, and Jan Likan, okay, was the lead. So he proposed this particular architecture called Linet 5, and this is the architecture, guys. Linet 5 architecture. Let me show you. If you have time, you can go through the paper, guys. But first of all, let me show you the architecture. See, this is the architecture of Linet 5. Okay, Linet 5. Now let me know, guys, whether you are able to understand this architecture or not. Let me take a screenshot and I'll take it on my board. Now it is understandable, guys. Tell me. So let's try to understand. See, first of all, this is the input image. And what is the size of the input image, guys? It's 32 cross 32. And there is no channel because this is the grayscale image they are using only for the handwritten document, let's say character. Then they applied something called convolution. Okay, they applied something called convolution. Now how many filters they're using, guys, in the first convolution layer? This is the first convolution layer, guys. Okay, now how many filters they're using? They're using 6 filters. They're using 6 filters, guys. Okay. And now you can ask me, what is the filter size? Okay, what is the filter size here? they're using 5 cross 5 filters, guys. Okay, if you read the research paper, they're using 5 cross 5 filters. See, this is the first architecture. Nah, this is the first research. So that time 5 cross 5 they used to use. That time 5 cross 5 they used to use. Okay, the 3 cross 3 actually came later on. 3 cross 3 came later on, but previously they used to use 5 cross 5 filter size. Okay, now if you calculate with that let's say formula I shared with you, the feature map you will be getting something called 28 cross 28 if you apply 5 cross 5 filters. Okay, then after that, where it is mentioned in the research paper. So I think here they have mentioned 5 cross 5, somewhere it is there. 5 cross 5, 5 cross 5. See, I checked it already. Linear 5, or you can just search here linear 5 filter size. You can see 5 cross 5 filters. Okay, even it is also available in the research paper, but as of now I don't remember the exact line where they have mentioned, but if you go through you will understand. Okay, got it. So 5 cross 5 was the first filter size. Okay, then they're using subsampling. Okay, they're using, guys, what? Subsampling. And what is the meaning of subsampling? Subsampling means this is the pooling layer, guys. Okay, this is the pooling. This is called pooling. And what pooling? They're using average pooling. Average pooling. If you go to the research paper, they're using average pooling. And if you apply average pooling, it will do the downsample operation and it will become 14 cross 14 and again 6 filters, because we are using 6 filters. Okay. Then again they're using convolution. Second convolution. Okay. So after applying second convolutions, here they're using you can see 16 filters. They're using 16 filters. Okay. And again it's a 5 cross 5, so it will become 10 cross 10. Okay, then again they will pass to the subsampling, that means average pooling, and it will become this one here 5 cross 5. Okay, 5 cross 5 and again 16 filters. Then they will do the flatten operations and they will pass to the fully connected layer. Okay, and at the fully connected layer, at the first layer they're using 120 dense that means neurons. Okay, 120 neurons they're using in the dense architecture. Then the second layer they're using 84 dense neurons, and at the last layer they're using 10 neurons, because it's a document classifications and they are having 10 different documents. Okay, 10 different character, that's why it's a 10. Output is equal to 10. Got it? Yes or no? See, diagram they didn't mention because in research paper, see, research paper things are like I mean in a different way, so everything they won't be mentioning in the graph because at the end it's a research paper, and definitely will be getting some difficulty whenever you are reading the first time. Okay, so JNAI का love course कब आएगा? Very soon I will announce what JNAI course, guys. Okay, maybe I can announce on my Udemy. It will come. Live course. Okay, live course. Yeah, I will also start the live project implementation, maybe playlist. Okay, on my YouTube channel. And generative AI, it is already available one playlist on my YouTube channel, guys. So there I already covered the entire generative AI. If you are completely new, you can check out that playlist. So there is a playlist called Generative AI Mastery. Okay, so it's a like big playlist. So let me show you. 2 videos are there. 10 hours and 10 hours. Okay, 20 to 22 hours I think recording I have done. See, Generative AI Mastery part 1 and part 2 are available. Okay, you can check it out. Okay. Now let's try to um, understand this architecture with the code. Okay, now we'll try to develop this architecture with TensorFlow. So again, I will go to my pooling layer. So do I need ML also for computer vision? If you know ML, theory understanding would be better for you, but if you don't know, it's completely fine. Okay, not required. See, Linear 5 is also very simple building architecture. Let me show you. This is the Linear 5 architecture, guys. First of all, sequential layer. Then at the very first, you can see we are having convolutional layer. How many filters? 6 filters. Okay. And what is the filter size? 5 cross 5. Here you can see. Convolutional layer, 6 filters, kernel size, that means filter size 5 cross 5. Padding is equal to valid, that means they are not using any kinds of padding. And another thing they have mentioned, the activation function they are using, they are not using ReLU, because that time ReLU was not available. They are using something called tan-h activation function. Okay, that time tan-h activation function were there. Okay, and the input image they are using 32 cross 32 comma 3. Okay, so here why I have given comma 3, sorry, it won't be comma 3, it would be 1. Okay, because it's a handwritten digit. Okay, that's why it's a grayscale image. Then in the second layer, they are applying subsampling, that means average pooling. So here we have done the average pooling 2D. So you have to import it. Here. After max pooling, you can also import average pooling. No, you can't change it to ReLU, because see, this is the predefined architecture. This is the predefined architecture. If you are changing it, that time it will not, you can't call it as a Linear 5 that time. Okay, no coder. And why they're calling as a Linear 5? Because it is having 5 layers. You can see 1 layer, 2 layer, 3 layer, 4 layer, and 5 layer. Okay, so this FC layer they're considering as a 1 layer. So that's why it's a Linear 5. 5 layer it is having. So one convolution, one average pooling, another convolution, average pooling, then one FC layer. Got it? Because these are predefined architecture, you can't change anything. If you're changing anything, that means it will become your custom architecture that time. Okay. See, there was a competition called ImageNet competition. Okay. So if you create any kinds of architecture, let's say that time if anyone is creating any kinds of architecture, they used to train with ImageNet data. Okay, and they used to evaluate the model, and whatever model was giving, let's say, good accuracy, that model was considered it's a state of the art model that time. Okay, so there is a benchmark data called ImageNet. So going forward, you will be using pre-trained model, transfer learning model, right? So that time ImageNet dataset you have to use. Those are the model is already trained with ImageNet data. Then average pooling, and what is the pool size, guys? So here you can see the pool size they are using. They have mentioned the pool size, FMHR maps, pool size in the research paper they have mentioned. Yeah, it's 2 cross 2, stride is 2, because this is the common thing. Okay, if you see everywhere, pool size would be 2 cross 2 and stride would be 2. And again, padding is equal to valid because you are not using any kinds of padding. Okay, then another layer after subsampling, that means average pooling, they're using another convolutional layer. Okay, another convolutional layer, and they're using 16 filters. Okay, so you can see convolutional layer, 16 filters, filter size is 5 cross 5, padding is equal to valid. Okay, padding is equal to valid, that means they're not using any kinds of padding, and activation is equal to tan-h activation function. Then again they applied subsampling, that means average pooling. You can see again they applied average pooling. Okay, average pooling, and this is the pool size. 2 cross 2, stride is equal to 2, padding is equal to valid. Okay, that means no padding. Then once it is done, they are doing the flatten operations. Okay, so here you can see flatten operations. Then they're adding the dense layer, that means FC connection. Okay, now at the first layer they're using 120 neurons. Okay, you can see 120 neurons are there. 120 neurons are there. In the second layer they're using 84 layers. 84 layers. Okay, and 10H and 10H activation functions. And at the last layer they're using only 10 neurons. Okay, and they're using something called softmax activation function. And this is the entire model summary. This is called Linear 5 architecture, guys. Okay, Linear 5 architecture. Yeah. Now, if you open any other architecture, let's say there is another one called AlexNet. AlexNet is also architecture, guys. CNN architecture. So this thing also you can develop. You can go through, guys. This task I will give it to you. Just try to understand how many filters they are using, how many convolutional they are using, how many pooling layer they are using. You can understand by seeing this particular graph. Okay, and let me also show you the architecture code. Let me just write AlexNet. AlexNet architecture. This is the AlexNet, guys. And what is the improvement in the AlexNet? They're using some other layer like batch normalization. And the activation they're using is equal to ReLU. Okay. And now they've introduced the filter size is equal to 11 cross 11. Okay. Then 3 cross 3. Sorry, not 3 cross 3, 5 cross 5. Then 3 cross 3. That means they're using 3 kinds of filter. One is 11 cross 11. Another is 5 cross 5. Another one is 3 cross 3. Because see, every architecture is having different kinds of variant. Okay. That's why they're naming it like AlexNet. They're naming it as a LeanNet. They're naming it as a ResNet. They're naming it as an Inception. Okay. That's how. Because it's a completely research. Okay. They did multiple research and they came up with this kinds of architecture. And this architecture was working better with that kinds of data. Okay. That's why. So this is called AlexNet architecture, guys. Even AlexNet paper is also there. You can search AlexNet research paper. Okay, you can open the research paper. You can also understand the architecture. Okay, very simple. I think I showed you how we can understand the architecture. Okay, layer by layer you can understand, and you can see how many filters they are using. What is the filter size? What is the image input size? What is the filter size? How many strides they are using? Okay, everything they have mentioned in the research paper. So this thing you don't need to memorize, guys. Okay, you don't need to memorize. These are the thing. It is already available. And for AlexNet, you have to import these are the library. So today I'm not going to show you any kinds of training, guys. Training I will show you whenever we'll be entering into the transfer learning. But before transfer learning, I'll show you how we can train our custom architecture. Okay, on top of the data. That time I'll show you okay how we can train this kinds of architecture. Then we'll try to move to the this one, our transfer learning approach. Okay, we'll be downloading the pre-trained model. On top of that, we'll try to do the fine-tuning operations. This is the idea. So yes, guys, this is the concept of pooling layer, and some few architecture we also understood. Okay, like Linear 5 and AlexNet. Okay, now you can explore over the internet. There are some like more architecture are available. You can open the like diagram and you can understand. Okay, how many layers they are using, how many filters they are using. Okay, what is the kernel size? Each and everything they have already given. And based on that, you can also create your own custom architecture, guys. Okay, so I'll suggest you guys at least try to create 2 to 3 architecture from your side. At least create 2 to 3 architecture. Your own architecture, guys. Okay, you don't need to follow any research paper. Try to create your own architecture. And I think you already know the flow. Okay, how we can create our own architecture. Okay. Then later on, I will show you the training process. You can train your own architecture. You can observe the accuracy. So can you do that, guys? Tell me. Can you do that? Because unless and until you are not practicing, things would be difficult for you. So I want you to practice. Okay, so guys, I think we are done with today's class. Now, let's connect in the next class. Okay, next class we'll try to understand the next concept, which is nothing but backpropagation in CNN. Okay, yeah. So thank you guys. I'll share all the materials, okay, in your GitHub, and link would be available in the description. From there you can check it out. With that, thank you so much guys, and support my channel. Try to subscribe and try to like. And if you guys support my channel, definitely I'll get more motivation to bring these kinds of content. Okay. With that, thank you so much and good night everyone. Bye. Thank you.